Okay, let's do one kind of clever, tricky one. Remember what your tools are. You got the work energy theorem, you got your definitions, you got your pictures. So we draw that. We have to understand the question. Here's a case where I've got this surface drawn in black here, and it's straight on these sides, but then it goes into this circular arc here. And the arc has a radius of A. So remember, you always kind of want to give your givens here. And the spring, it's attached to a spring here. These guys are attached. Bolt that together. Spring has a spring constant K. Radius is A. The mass of this block on the end is M. And what we want is the work due to that force equal to whatever. But that force is variable. So what else is given or implied in this? Well, the problem statement, if we do this slowly. Now granted, if it starts at rest, we got to get it going, but if we do it slowly, we're not changing the velocity very much. And that's a concept that comes up a lot in thermodynamics, okay? We're doing it very gradually, nearly zero velocity, okay? So we've got that. So what's implied here is that V is equal to a constant. Okay. All right, so we're going to set this up, and that's a little tricky. If they say, let's see, in this problem, it's variable forces maintain tangent to a frictionless, frictionless, so it's not really frictionless, negligible friction, surface. By slowly varying the force, a block of mass M is moved, and the spring is stretched from position 1 to 2. So we need our states. We need state 1. It started here and ends up here. Cool. And the spring has negligible mass and a force constant K. The end of the spring moves along that arc. Yeah, calculate the work done. So you go, hey, I'm going to use the definition of work. So I'm going to go, the work due to F is equal to the integral of F dot ds from 1 to 2. And then that's by definition, right? And then I go, oh, I'm not liking this already. What can I say about the F? And you might go here and you go, well, I'm pulling against that spring. And I'm not changing the speed. So maybe my pull is exactly equal to the spring pull back. Because this is the unstretched spring length here. And then, so maybe my F is just the spring force, opposite. That can be when you stretch a spring out. That's wrong. Why is that wrong? I thought I could go through here and do all this. Well, wait a minute. Not only am I working against the spring force, I'm working against gravity because I'm lifting it. And now I'm going, oh, seriously? Okay, I could draw. I got a normal force, I got an mg, I got a spring force, and I got me. They should add to 0 because I'm in dynamic equilibrium here. All right, I could do that. I could try to deal with it. But wait, we've been using energy because it was kind of nice. So how about let's can that idea, and why don't we try something else? What if I say, let's see, the work due to all non-conservative forces causes a change in E, right? So that means that this is E2 minus E1 is the work non-conservative 1 to 2 for all, right? All right, fine. Let me take a look at this. What have I got at 1? Well, I'm going to, whenever you're changing height, you need to set that h equals 0 point. So I'm going to define that as h equals 0. It's a constant v, so I could say that's, in this case, 1/2 mv squared, where v1 equals v2 equals equals V. And I got no potential energy, so I'm done. All right, and what have I got at 2? State 2. Well, all right, it's state 2. Let's draw that here. I've got 1/2 mv2 squared, but those are the same. Hey, we knew no change there. Plus mgh2. And so we just take a look at that. Now I can tinker with that all we want, right? So, constant speed tells me that. I've got mgh2. Maybe I want to find out what that is. I'm just exploring. Every thought I have, I kind of write it out here. So I go like this. It's along a circular arc. It's up here. There's my h2. Here's my h1 equals 0. My h2 is at this height. I should do it this way. It's that length right there. This is theta 2. This is A. Hey, that's not so bad. This height is going to be A sine theta 2. All right, cool. So I got M, G, A sine theta 2. Did I do that right? I think I did, right? That's state 1, no height. State 2, I get higher up there. And the same speed, so no change in kinetic energy. All right. Well, I've kind of been avoiding the issue, haven't I? Now I've got this guy. Okay. Let's see. Let me go over here. What didn't I do? You see it? I'm giving you time here. Just nod your head past this. You got to think it through. I didn't really show all the forces. What are the forces here? I got gravity, so I've handled that here. I've got normal, but that is perpendicular to the motion. So I've got, let's see, the work due to the normal force. That's 0. Gravity's handled over there. That's a force in interaction. I've got my force here that I'm applying. That's cool. That's what I want. Oh, wait, I've got a spring. So do I do it over here or over there? I need to do it over here, don't I? So let's see. What's the potential energy of the spring at state 1? Well, it's not stretched, so I don't need it. But what's the potential energy of the spring at state 2? Well, that is 1/2 k times that stretch, S2 squared. Oh, boy, I didn't get that in there, right? Why didn't I get it in there? Because I didn't stop and say, what forces are there? Because ultimately, energy is talking about the forces, the interaction, but in a really cool, efficient way. So let's not make that mistake. We've still got this is still good. We've still got that, but we've got this plus 1/2 k S2 squared. Now, how much is S2? We're getting pretty close. Hey, did you see this over here? Right, we kind of bounce around, right? But we leave cookie crumbs as I problem solve. I'm going to go, whatever I can say. Look, I got the normal force, fine. That's what I want. I got gravity force, and I got a spring force. And if you look up there, that's all that's there. And so I'm left with this. Hey, I did a little trig to get that guy. What's S2? Well, let me just draw that. Where is this? That's that length right there, S2, right? And this angle is theta 2, and that's A. And so we're going to be moving into rotations very quickly and looking at that relationship. You know the circumference of a whole circle is 2 pi times r. So the arc length is the fraction of the angle in radians. In this case, r is A. So then if you do that in radians, and you must do it in radians, then the answer for us is theta in radians times A. What did I? That's the answer. That's the answer. We're going to get into that relationship pretty soon. So that was generally would be a hard one. I wouldn't put it on a test because I know what the results would be. But seeing it's pretty neat. We started by looking at the definition for work, and we could have made a really easy error in assuming that my force was exactly balancing the spring, neglecting the force of gravity. So I said, oh, I'm going to bail on that unless I could figure out how that varies. It's, maybe. But let me just try something else first, namely this. You've got definitions, you've got this. Work energy, okay, fine. I got my states, and then I looked at 1, and I looked at 2, and I looked in between. And the key to not missing it was not to leave out the forces. I've got a normal force, which I can see. In this case, it's doing no work. I've got a force of the hand. I've got a force due to gravity, and then I've got a force due to spring, right? 1, 2, 3, 4. So I've got to account for these. These guys showed up on this side of the equation. And these guys I handled on that side of the equation, right? And if there was friction, yuck, because the angles and yuck. But maybe I wouldn't even have to go here. I'd just solve it here. All right, so that's a good example. We are next going to look at the relationship between conservative force and potential energy, integral derivative, and graphs. And then we will talk about power, efficiency, and also intensity, which is related to power. And the rest will be up to your practice and reading and so on.